So, hello, good morning. So, today we will continue our discussion on integration. So, in the last class, I told that integration is the technique to find area under the curve, and we have also seen how to compute area under the curve. Now, let us take a function, mathematical function. Let us see how to calculate area under the curve. Now, the function I will take is, let us take a function x square. I am taking the function x square. So, let us say my f of x is x square. So, this is the function I am taking. Now, I need to find out area under this curve from x equals to, let us say 0 to x equals to, let us say 5. So, now from x equals to 0 to x equals to 5. So, up to here I am taking. Now, let us see first how the function looks like. Now, this is your x and this is your y, or f of x, you can say. This is your f of x. As you change x, f of x goes like this. See, because it's f equals to, so as I increase x, f of x also increases, and it's x square function, so it looks like this. It will go like this. So this is how your function changes with x. So now this is how your function changes with x. So now you want to find area under the curve from x is 0, maybe x is 0 here, and maybe x is 5 here. So at x equals to 5, your f of x value will be, say, that is 25. And at x equals 0, f of x value is also 0. Now you want to find area under this curve. So area under this part. Area under this part you have to find. Area under this part. Area under this part you have to find. Then to find area under this part, first you have to divide a whole area into a small pieces. Let us see how I do that. If this is the area, then you have to divide total area into small pieces like this. This is some small piece, and you have to make such a small pieces, then you have to add area of each piece. So for example, this value at this point, x value is x, then f of x will be f of x, let us say, that is x square. F of x is x, let us write down here clearly. At x equals to x, your f of x is x square. Now I am going to take one more point, that is x plus delta x, that is very near to x point. As I go from x to x plus delta x, I don't find much change in x square. X square will be almost common. Then to find area under this part, I can write down x square delta x, because x square is the value of f of x at x is x, and now that grid size is your delta x, and this will be my area under that small part. Let us write down, that is, I can write down it as small area, let's say dA. So if I take limitation here, then to find net area, I need to integrate, or I need to add all the such small areas, and that goes from I equals to, or x equals to 0 to, let's say 5. Then if I take limitation here, as I told in the previous class, if I take limit delta x tends to 0, your number of grid points will be infinity. In that case, you can replace this by, you can write down the same thing as a equals to integral from 0 to 5 x square dx. So this is what you will get. This is what your area. Let us try to find out what is that. So I will come from the differentiation first. If I take differentiation, that is, I am taking one function here. Let us take one function. That function is, let us say, I am taking, let's say, g of x, x equals to 3x power, or I can write down 1 by 3 x power 3. I am taking this function. Now I am taking one function, that is g of x equals to 1 by 3 x power 3. So now if this is the function, if I find dgx by dx, so that will be 1 by 3 is common. Then for x power 3 I can write down 3x square. So this is what I get. So this is what I am getting from differentiation, the result from differentiation. Then now dg of x by d of x equals to x square. This is what I get. Now from here I can write down dg of x that equals to x square dx. Now here x square dx is, you look at this part, x square dx is this part, x square dx is this part, that equals to area under x square curve when you change x from x to x plus delta x. So that is what this one. Now if I integrate, if I sum all, this is the small area, this is the small area under x square curve. When I integrate this one, I get integral dg of x that equals to integral x square dx. Now I want to integrate the function from 0 to 5. Here also you can take from 0 to 5. But when I integrate, because g of x is the, or dg of x is the small area under x square dx curve, when I integrate I get full area, and that full area will be g of x. That full area will be g of x, and that will be equals to integral x square dx. You can take even boundary conditions from 0 to 5. Now see what is g of x here. I can write down here boundary conditions from 0 to 5, because this is also going from 0 to 5. So now integral x square dx from 0 to 5 equals to g of x. Now I can write down here once again, integral x square dx from 0 to 5 equals to g of x. Then the conditions, the boundary conditions are from 0 to 5. Now let us see what is g of x here. The g of x I have taken, that is 1 by 3 x power 3. 1 by 3 x power 3. So let us fix here. So now 1 by 3 x power 3, then my boundary conditions are going from 0 to 5. And in this 1 by 3 is constant, then you can take it out. Then now x power 3, then boundary conditions are 0 and 5. That is 1 by 3. Then when you apply boundary conditions, you can write here 5 power 3 minus 0 power 3. Then 5 power 3 is 125 minus 0, then you get 125. So here the answer is 125 by 3. So that equals to, you can write down it as 1.7 roughly. So this is your answer. So your answer is 41.7. So that is the area under this curve, area under this part. So this is how you can integrate the function. So now let us take one more function. I am taking now my function. The function is, let us say f of x equals to, say, sin x. I am taking the function f of x equals to sin x. Now if I take f of x equals to sin x, if I draw the graph, then I get something like here. So this is the function, this is my f of x. Because f of x equals to sin x, then x is going this way. When theta is 0, when x is 0, then f of x will be 0. When x is let's say pi, again you get f of x is 0. When x is 2 pi, you get the same. But when x is pi by 2, you get maximum, that is 1. When x is 3 pi by 2, you get again minimum, so minus 1. So this is your sine function. Now I need to find area under the curve, area under the sine curve from, let us say, 0 to 2 pi. From 0 to 2 pi means from here to here. So this will be your area. You have to add this area and that area. Let us see what is that. So that you can write down as f of x or sin x dx integral that goes from 0 to 2 pi. So this is what the meaning of this. Finding area under the curve from here to there. So mathematically you can write down integral sin x dx, and integration is going from 0 to 2 pi. So now let us come from here. So if I take d by dx of cosine x, so d by dx of cosine x will be minus sin x. D by dx of cosine x is minus sin x. So now I can write down here d of cosine x equals to, or minus d of cosine x equals to sin x dx. Now sin x dx here in this equation, sin x dx is area under sine curve when your x goes from x to x plus delta x. So this is what your sin x dx is. So now, and this one is your the area under sin x curve So now here d by dx of cosine x is minus sin x. So if I take d cosine x or minus d cosine x will be sin x dx. And here sin x dx is area under sin x curve when your x goes from x is x to x is x plus delta x, and that is equals to this part minus d cosine x. So if I integrate this one, if I integrate sin x dx from 0 to 2 pi, then I will get my full area, and that full area will be integral from 0 to 2 pi, I get minus d cosine x. So because d cosine x is a small part of your area, if I integrate d cosine x, you will get full area, and that will be equals to cosine x. So now boundary conditions are from 0 to 2 pi. So now let us apply boundary conditions here. So if I apply boundary conditions 0 to 2 pi sin x dx v2 minus, let us fix first cosine 2 pi, that is what I am putting upper condition first, then lower condition, that is cosine 0. Now cosine 2 pi value is you can even see this graph. Let us draw the graph here. This is the graph for cosine function. So when cosine 0 is 1, cosine pi by 2 is 0, this is pi by 2 and this is pi, and 2 pi, cosine 2 pi is 1, cosine 2 pi is 1. So now 1 minus, cosine 0 is also 1, so let us take 1 minus 1. So 1 minus 1 is 0. So you will get the result. The result is here, integral sin x dx from 0 to 2 pi will be 0. So area under sin x curve from 0 to 2 pi is 0. So even see graphically here, you will get the same result. Look at this result. Here I am going from, here I am taking sine, this is the sine function. Now I want to integrate this function from 0 to 2 pi. When I integrate the function from 0 to pi, and that I am getting the positive area because here positive values are there. And when I integrate the function from here to there, I get a negative area. Then the whatever area I get positive area, that the same amount I get negative area also. So if I add that positive and that negative, I get 0. The same result is consistent with even graphical model. So now this is the result. So this is how you can find the integration. So tomorrow we will continue from here.